Much like with resistors, capacitors can be arranged in series and in parallel, and it can be useful to find the equivalent capacitance. So, are these capacitors in series, in parallel, or neither? We know that they are not in series because a charge that leaves the battery can go into one capacitor or into the other, but doesn't pass through both. And we know that series is when a charge passes in series, repeatedly one right after the other, after the other. They are in fact in parallel because there are two paths they can take, and that these two paths are each directly connected to the battery. All right, because each capacitor is connected directly to the battery with an EMF of E, the potential difference across these is the same and is equal to E. And that's what we want with the potential difference across the equivalent capacitor, because we're going to try and replace this with a unit that looks something like this, where we still have capacitance E, but we also have C equivalent. This implies that the charge on each capacitor is not the same, unless the capacitances happen to be equal. Instead, we know that the charge on 1 is C1 times the voltage difference, and the charge on 2 is C2 times the voltage difference, and the charge on the equivalent capacitor would be C equivalent times the voltage difference. Of course, with the actual capacitor, the total charge that leaves the battery has to be the sum of these, that Q is Q1 plus Q2. But for the equivalent capacitor to be, well, equivalent, then it has to draw the same charge. So Q equivalent is also the charge that leaves the battery, and therefore is Q1 plus Q2. And then we substitute in. We know the charge here was C times delta V for each of them, but the delta V's are the same. They're all the EMF of the battery, and so we can divide that out and get that the equivalent capacitance is the original capacitance 1 plus 2. That is, parallel capacitors add directly, the same way that series resistors added. Notice the switch, though. We've switched both resistor to capacitor, but also series to parallel. Now we have capacitors that are in series. There's no option for a charge that leaves the battery. It comes and must land here. It's a little stranger, though, because it can't hop and go on. Instead, what happens here, the charge that ends up here can't get to the rest of the capacitor. It's blocked by that gap. That's what makes the capacitor a capacitor. But imagine we have this. Plus Q leaves and gets stuck on this upper plate. But because of that, it repels negative charge, repels the equivalent positive charge down here, pushing it out, so that we pick up plus Q on the top, but then we pick up minus Q on the bottom, making it the capacitors we're used to, equal charges of opposite sign. And this plus Q that was omitted gets down here, but then gets stuck on this plate. And so we get plus Q on this plate, which then dries out a minus Q down, or dries out a plus Q that goes around and back to the battery, leaving us minus Q. The key thing from all of this that you have to keep in mind is that the capacitors end up having equal charge. All right, not the equal potentials, but equal charge. And of course, that would have to be the same charge that you get on the equivalent capacitor, because it has to be equivalent. So we can say that the delta V, the voltage difference across each capacitor, is its own charge over its capacitance, right? But the total potential drop has to be the same sums for 1 and 2 to give us the equivalent. So we end up with something like this, that delta V equivalent is delta V1 plus delta V2, but each of those are their charge over their capacitance, but all the charges are the same. So we can cancel out that common charge, and we get, maybe not surprising at this stage, that the 1 over this equivalent capacitance is 1 over the original C1 plus 1 over the original C2. Or to say, series capacitors add inversely, meaning they look a lot like parallel resistors. That leads to this unfortunately complicated chart that might be useful or not. I think the easiest way to do this is to remember that series resistors add directly, and that every time you change something, you also change what's happening, how they add. So if you change from series resistor to parallel resistor, you go from directly to inversely. But if you take series resistor to series capacitor, then you also become adding inversely. And if you do both, then you're back to adding directly. However you remember it is sort of up to you. It comes down to, way back when, that we defined the voltage drop. We defined resistance as such that the voltage drop is I times R, but we defined capacitance as such that Q equals CV. So notice that we have V alone on one case and V paired with somebody on the other case, and that makes 1 over that makes 1 over capacitance useful, or really 1 over what's called a conductance. For truly horrible historical reasons, conductance is usually symbolized by G. So that's sad, but then we would get that the current is G times V. And if we did that, then conductance and capacitance would add in the same senses.